Next, we'll solve a problem. A chain of mass m, length L is kept in three different positions as shown. Find the energy of the chain in all the three cases. Okay, so this is the question. It has three parts. So first one is this. So this is a ground and you have the chain being placed on ground. Okay, that is part A. Then we have part B. This is ground position and the chain is placed somewhere here. Okay, and this height is given. So this height is h. And we have a third case. This is C. The chain is placed like this. Okay, the question is find the potential energy or find the energy of this thing. Right? Since the chain is not moving, it is obvious that they are asking the potential energy, even if they simply mention that find the energy. Okay, so coming to the answer, part A question. So the height is right. What's the equation for potential energy? U is equal to mass into gravity into the height. So now you see it's present on ground. So it means height equal to zero in this case. I can write h equal to zero. So h equal to zero means the potential energy U is equal to m into g into h equal to zero. So there is no energy. Part B question answer. So the height is h, right? So this means the potential energy is there is a mass m, g is right anyway. Since they are not giving any values, we can simply write mg into h, right? Doesn't matter what is the length L for this. Okay. Now you see, in the third case, the height is equal to again, so the complete chain is not at a height h. So in such cases you will always represent the mass to be concentrated at the center of the object. Okay, now the total length is L given. So what is this height of this, the center of mass? That will be the length by 2. You see they have mentioned clearly that there is a length L. So total length is L, total length of the chain. So h is equal to, in this case, it becomes L by 2. So this implies U is equal to m into g into L by 2. Half mgl is the answer. Okay, moving ahead. Next question. The potential energy of certain body at a position, say A, is minus 40 joules. Then, okay, the work done by a force in moving this body from A to B is minus 20 joules. So now the question is find the potential energy of the body at B. What is the potential energy of the body at B is the question. So here we use the formula, that is the work done in moving any objects, say A to B, is equal to negative of the change in the potential energy. This is the work done. That is equal to minus of the potential at B minus the potential at A. Okay, so simply we can write this is UA minus UB. So if we want to find UB, keep UB on this side, move this to the other side. That is UB is equal to UA minus work done A to B. So this is minus of 40, minus of minus is plus 20. So minus 20 joules is the required answer. All right. So like this, we can solve the problems based on the potential energy. Let's move further. Next, we'll look at the concept of equilibrium. And now the definition of equilibrium already has been seen, right, in the forces. But now we'll look at the types of equilibrium. So there are three fundamental types of equilibrium. Now, fine. So what is the condition for equilibrium? A body is said to be in equilibrium if the net force acting on the body is equal to 0. So equilibrium means the net force acting on a body equal to 0. So that means I can write F net equal to 0. Right. But let us assume that the forces are conservative in nature. Right. So if all the forces are in nature, if they are conservative, definitely this equation holds good. That is, force is equal to minus of du by dr. All right. Then I know that then all the forces result, right? If the result is 0, then it is in the equilibrium. So we want to say that equilibrium means F is equal to 0, right? So therefore, if I say F is 0, this implies negative of du by dr is 0. In other words, I can say simply du by dr is equal to 0. At equilibrium, the see u is the energy, right? And du by dr is differentiation of the uh, potential energy with respect to the distance. All right. So when I say du by dr is equal to 0, this is the condition that has to be met at equilibrium. That is, if you try to plot a UR graph, right, then the slope of the U graph at a particular position has to be 0 because du by dr is the slope of the UR curve. All right. Okay. Now let us see. This implies at H equilibrium position, the slope of the UR, okay, I'll write it smaller. The slope of the UR graph is 0. Right. So now we will go back to the fundamental equation, right, that we might have studied in mathematics. So it says that you have a curve, we have a curve y is equal to f of x. So let me write it over here. So if y is equal to f of x is a curve, right? Then if you say dy by dx, differentiation is equal to 0, right? This implies at this particular point, right? Either you have a maximum point, right? This is maximum, or it is a condition for minimum, or it is a condition for 0. If y is 0, dy by dx is still 0. So we have one of the three conditions to be met. So if at all I say that du by, now we'll extend the same point, right, to our discussion that is about the UR graph. So if the UR graph differentiation is 0, du by dr is 0, the point that we need to understand is either at that particular point where the slope is 0, either the curve is attaining its maximum. Okay, otherwise it's what you call value will be minimum. Otherwise, the u is equal to 0. One of the three conditions has to be met. Right? So depending upon, right, what type of, is it maximum, is it minimum, or is it 0? Depending upon, we try to uh, extract three different conditions of equilibrium, right? So based on whether it is taking a maximum value, minimum value, or right, uh, 0 value, you can try to extract the three different values of three different types of equilibrium. All right, I'll come to that point. So, uh, okay, at the equilibrium position, the slope of the UR curve is 0, or I can write, or the potential energy is, therefore, it has to be either maximum, or it can be minimum, or it can be a constant, right? Because differentiation of a constant is also 0. That's why, right, we can say that it can be a constant. Now, there are three types of equilibrium possible. The first type is called as stable equilibrium, second one is unstable, and the third one is called as a neutral equilibrium. All right, let's come to the types one by one. Okay, the first equilibrium is, let's say, stable equilibrium. Let's consider one diagram so that it becomes very clear. All right. Now, uh, so this is the example. We consider uh, a small ball is placed inside a smooth spherical shell. So the bigger ball, what we can see, bigger circle is corresponding to the spherical shell. Inside that, we placed a ball. Okay. Now, at this particular position, it's very clear that the system is stable, right? This is in equilibrium and it is a stable equilibrium because unless and until we move either the outside shell or the inside ball, the whole system is not going to move. It is fixed. All right. So this kind of equilibrium is considered to be stable equilibrium. It's a stable one, right? Fine. Then let us move to the second case. This is called as unstable. I'll give a very similar example. Now we consider that I'm placing the smaller ball over here at the top, right? So in this case, you can see that the ball is placed over the smooth sphere. Over the smooth sphere. So I know that, right? At the moment you leave this, it looks stable, but immediately after some time, the ball will fall down. So this is unstable equilibrium position of the ball. Okay. And the last one, the neutral equilibrium. So let's look at the neutral equilibrium. It's a very simple case. Let us say this is the surface and place a ball. We place the ball on a completely horizontal surface, right? So we'll give that example. Smooth, horizontal ground, or some surface, right? That is considered as the neutral equilibrium. Right. Now let us look at, let us compare, let's try to compare all the three uh, types of equilibrium now. So over here, let us try to write. Okay, so this is corresponding to the stable equilibrium. Here we are going to write the points corresponding to unstable equilibrium. Here we will write the points corresponding to the neutral equilibrium. Okay, so the first point is that in all the three cases, what is the net force, right? Since it is equilibrium, definitely the net force equal to 0. So same thing I'll copy. Okay, so that is net force equal to 0. Net force equal to 0. So there is no doubt about this point. So the net force acting on, right, the balls under this condition is equal to 0. Right, let's move on to the second point. Right. Okay, here, if the system is in stable equilibrium, right, definitely it also has to satisfy another condition, right? That is the condition we saw earlier, that is the du by dr has to be 0, which means slope of the ur graph is 0. It holds good even for all the other two types of equilibriums as well. So that is du by dx is 0, du by dx equal to 0. Okay, so first two conditions are same for both. Then is there any difference between these types of equilibriums or not? We'll find out. Okay, let's move further. So the point number 3 is that now let's talk about the stable equilibrium. When displaced from the equilibrium position, let's say I slightly distract the equilibrium condition. The system is in equilibrium, stable equilibrium. I distract that. I slightly push the outer surface. Okay, whenever, right, when displaced from its equilibrium position, a net restoring force starts acting on the body, which has a tendency to bring the body back to the equilibrium position. You see that it will come back to equilibrium as quickly as possible, right? So that's the point that we are going to write under the stable equilibrium. So this is, say, when displaced from the equilibrium position, what happens? A net restoring force starts acting on the body. So a net restoring, a net restoring force is going to act. So I'll write starts acting on the body, on the body. So what is the tendency of this particular force? So that is, I can write, which has the tendency to bring back. It will try to bring back the equilibrium. All right. So that is the point we are going to make for stable equilibrium. Now, looking at the unstable equilibrium, just imagine the diagram we draw here, right? A ball, smaller ball is placed on the top of another larger ball. When you slightly try to distract the equilibrium, net force starts acting on the body, which moves the body in a direction of displacement or away from the equilibrium position. It will never attain the equilibrium back. So that's the ultimate point. Okay, so we'll write up that point over here. So that is when displaced from the equilibrium position, a net force starts acting on the body to move it away from the equilibrium condition. It will never attain the equilibrium because it is trying to move the body away from the equilibrium. So it will never attain the equilibrium back. So that is the point. Okay, let's move further. What happens when you try to distract the equilibrium of a neutrally equilibrium object which is in the neutral equilibrium position? Okay, right now we will see that. Okay, under this third column we are going to write, let us say we try to displace the object in neutral equilibrium. Body will have no tendency to uh, come back to the original equilibrium position, or it will try to move away. Okay, it will never be in that because it will in the uh, it's as soon as you move it the body's condition from equilibrium, that condition is once again the equilibrium. It will try to be in the same state until and unless some other force tries to stop them. For example, a ball is placed on ground, smooth horizontal surface. You push the ball away, means ball will start moving in a specific direction. It will not stop if there is no gravity, no other forces. It will not stop. It will be in the same state of motion. So that is once again, as soon as you distract the object from equilibrium, it attains immediate equilibrium once again. The new state is also equilibrium. That's what is the difference uh, of the neutral equilibrium with the other two. Okay, so let's write that point over here. When displaced from its equilibrium, the body neither has the tendency to move away nor to come back. To the equilibrium. This is because it is again in the equilibrium position, right? I can write it is again in the equilibrium condition itself. So that's the very fundamental difference between the three cases. Now let's go ahead and make some more comparisons. All right. Now this was the point number 3, I guess. Let's move to the point number 4. Okay. So the point number 4, while comparing the three types of equilibriums. Now comes the difference part. the potential energy, I'm talking about the stable equilibrium now. The potential energy in the equilibrium position is minimum because it is at the lowest point, right? I had a position of this object over here, which is minimum, right? If you have an object here, slightly bigger value. If you have the object here, much bigger value. Object here is biggest, highest value. So you see that in the equilibrium position, which is corresponding to the stable equilibrium, we can make a comment that the object has minimum potential energy compared to its neighboring positions. Any point near to the current location has more energy compared to the present value. So that's the very important difference. All right, so I can write the potential energy in the equilibrium position. In equilibrium position, whatever is the potential energy that the object has, right, is minimum compared to the neighboring points. So whenever a point is minimum, right, this is what is the equation. The d square u, double differentiation, d square u by dr square has to be a positive quantity. Just to identify whether it is a stable equilibrium, differentiate u with respect to r twice, and if you get a positive answer, yes, it is the stable equilibrium. At the same time, let's try to write a point under the unstable. Unstable means, right, recall the diagram, it is somewhere here. So this is the highest point on the surface. Highest point means highest energy, correct? So because of the energy is highest, this is unstable. Excessive energy you have, so which makes the system to be unstable. All right, so now the potential energy in the equilibrium position, is maximum compared to its neighboring points. So that means it is a highest point. So d square u by dr square has to be a negative quantity. It is negative means the current position is highest. Okay, fine. Then let's move to the next one. The neutral equilibrium is a condition where the potential energy, you see it was a horizontal surface, right? It is here or it is here, no change. Potential energy is a constant. So if the potential energy is a constant value, right, irrespective of where the object is present, right, then that kind of neutral equilibrium says that potential energy remains constant. Okay, so PE uh, remains constant. So that means the d square u by dr square is going to be 0. Right? One more point we can write here as a comparison. So here, when in case of we are talking about the first column, that is a stable equilibrium. When displaced from equilibrium, center of gravity of the body goes up because it's in the lowest position. When you try to displace the object has to go up. So because of that, the center of gravity of the body goes up. All right, so that's the next point that we are going to write in this comparison. Okay, so I can write this is the point number 5. When displaced from equilibrium, the center of gravity short form is COG, center of gravity of the body moves up. So the body center of gravity COG moves up. At the same time, for the second case, in equilibrium, it is at the highest position. As soon as you distract, the COG comes down. Okay, so same thing here, right? When displaced from equilibrium, the COG, center of gravity of the body, comes down. When you can see that in neutral equilibrium, center of gravity of the body remains same, right? So I'll just write COG remains the same, same level, right? It's not going to move. Okay, now let's go to a problem. Find the directions of forces at A, comma B, comma C, comma D, and E on the graph. So there is a graph given. From that we have to answer this. And also this is part B of the question. Find the positions of three types of equilibrium. Right. So the graph given is like this. Point A, this is the point B, this is the point C, point D, point E. Okay, also the time axis has been marked. This is 2, this is 4, this is 6, and this is 8. Okay, so this is the distance x versus u graph, not time. Okay, so displacement x in meters, and the u, that is the potential energy. Right, so I need to identify the direction of the forces, right, at a particular point. Right, I know that the force is equal to minus of du by dx. All right, so it's a negative of the slope of the ux graph. Let me write that point very clearly. So I want to find what is f. F is equal to minus of du by dx, which is nothing but what is du by dx? Slope, negative of the slope of ux curve. Right, so at point a, okay, check out what is the slope. Slope in the sense, is your graph increasing after point a or decreasing? It is increasing, right? At a, right, du by dx is what? It is positive. So this implies the force is expected to be negative. That's all. So the negative means it is towards left, right? Otherwise, if it is increasing, you can say that it is to the right. So plus minus, we know the same thing. Like that, you have to fill for d. What is du by dx and what is f? Right? C, d, and e. This is our target. So now at b, no change, right? This is du by dx is positive. This means f will be negative. Now move further. At point C, you can see that after C, the curve comes down. So the du by dx is negative, which implies the force which we are talking is the positive. Come to D. D here also it is negative. Du by derivative is negative, slope is negative, which means the required force is positive. At point E, you can see that slope means it's horizontal. If you try to write a tangent, that's going to be parallel to the x-axis. If it is parallel to the x-axis, slope is 0. When slope is 0, the force is equal to 0. Okay, so we found that. Now, we are trying to answer to part B of the question, right? So where you have the energy maximum, energy minimum, energy zero, this is what we want to find. We start from this. Whenever you have a slope, you don't find that. Only the points where the slope is 0, I'll try to mark with the red. Okay, so this is a point with slope 0. Again, slope becomes 0 here. These are the 2 points. So I have to answer at which point you have what type of equilibrium. This is the question. At only uh, at at x equal to 2 and at x equal to 6. So first I'll answer at x equal to 2, right? At x equal to 2, I know that the potential energy is minimum. Okay, it says that the potential energy is minimum at x equal to, sorry, at x equal to 2, energy is maximum because it's at the highest point, right? So my mistake, I correct myself. At x equal to 2, the potential energy is maximum. I'll just write that. So at x equal to 2, this means the potential energy is maximum. Now you know that out of the 3 stable conditions, right? Out of the 3 equilibrium conditions, the unstable equilibrium is the one which has the potential energy highest. So that point at x equal to 2, we have unstable. Unstable equilibrium. Now at x equal to 6, at x equal to 6, the potential energy of the object is, you can see that it is minimum. We know from our previous table that if an object has minimum potential energy, that will be considered as the stable equilibrium position. as a stable equilibrium. Now, the question says is actually asks about all the three, right? Right? Find the positions of three different types of equilibrium. We could find only two, right? I also have to mention one comment here saying that, right, there is no point on this whole graph where the potential energy is constant. So we don't have any point of neutral equilibrium. So I can simply write no, I have to write a neutral. So there is no point on this curve. So no neutral equilibrium point on the curve. So we talked about all the three types of equilibrium.